much of the world is committed to transitioning to a low-carbon global economy by 2050. Carbon capture and storage, also known as CCS, is among the various approaches being implemented to help meet aggressive decarbonization goals here and abroad. The Geomechanics for CO2 Sequestration Challenge exemplifies new and innovative approaches for ensuring that the geologic storage of CO2 is done safely with no impacts to human health and the environment. The work being done here advances our ability to monitor and maintain secure storage by understanding with greater certainty how the subsurface behaves as a carbon dioxide storage reservoir. With CCS now poised to be a growth industry, this type of research is more important than ever. On behalf of DOE's Office of Fossil Energy and Carbon Management, I extend my thanks to Lawrence Livermore National Laboratory and the faculty, advisors, and researchers for their innovative thinking and contributing to this important area of research.
Welcome, everyone. We are the Geomechanics for CO2 Sequestration team. I'm Akshay Suresh, together with fellow researchers, Alex, Giuseppe, Han, and an accomplished group of faculty. We bring interdisciplinary expertise to tackle a challenging problem. Climate change is a reality affecting all of us today. Combating climate change requires us to pay off our enormous carbon debt, reaching carbon neutrality by 2050, and negative emissions thereafter. Renewable sources of energy, such as solar and wind energy, are futuristic, but cannot thaw away or chip away at our carbon debt. Biological reserves, such as forests and phytoplankton, cannot operate fast enough to avert human-made climate change, and therefore we need to act quickly ourselves. One promising avenue is geologic carbon sequestration, which we show in the bottom right figure. In this method, we trap the carbon dioxide generated in factories and power plants and store it underground as a supercritical fluid. However, one big concern here is that by injecting carbon dioxide or any other fluid underground, you increase the pressure in the subsurface, and that may lead to earthquakes. One notable example is earthquakes associated with underground fluid disposal in Oklahoma. In the figure on the right, the red curve shows the fluid disposal rate, and the black curve shows the observed seismicity in Oklahoma. Notice how the black curve shows a delayed response to trends seen in the red curve. And therefore, we have to play a very careful game. We need to store large masses of CO2 underground while minimizing the seismic hazard. And this is where seismicity forecasts enter the picture by helping us regulate the pace of injections to ensure safe commercial operations. In this regard, how well do existing seismicity forecasts perform? The answer is we have a mixed response. Here is a graph showing the time series of cumulative earthquake counts seen in Canterbury, New Zealand between 2010 and 2012. The black curve is our data. The colored curves correspond to various models that have been fit to the data. As you can see, the blue, pink, and gray curves represent are highly inaccurate. In contrast, the orange, green, and red curves are more accurate. However, these more accurate models are extremely slow, needing 22 hours of preparation time. They're highly resource intensive, needing supercomputers to function. And finally, most limitingly, one needs PhD level expertise to operate these models. Let us crunch some numbers to assess the seriousness of these limitations. To reach carbon neutrality, we estimate needing about 30,000 sites globally. If at each site, say that model tuning needs to happen once every 5 days, then we need about 6,000 analysts operating these sites. This number is about 60% of the global seismology community, and that would make current methods highly non-scalable. What if we could enable scaling with speed and accessibility improvements? Giuseppe will now tell us how our efforts address these concerns.
Thanks, Akshay. This is where our tool, SAFE, comes in, and our first most dramatic success. We've reduced the total time to construct a physics model from a whopping 22 hours to under 2 minutes, and that's just on a tablet. How do we do this? Well, there are 3 key ingredients. The first was to update the existing codebase to use best practices from numerical software, such as vectorization. The second was to reduce the complexity of the original physics model so that we could achieve the same performance with a fraction of the parameters. And finally, by using more powerful and more adaptive optimizers, our models are ready to go in just a few iterations. Now, beyond speeding up the code, these improvements also make the code quite modular, which is in turn a big win. All of the optimization and data processing is taken care of automatically and under the hood. This means you don't need a seismology PhD to run our code. Anyone with some programming experience and basic knowledge of statistics can now be empowered to generate forecasts. What's more, we're releasing both our code and our data open source, so the public is free to learn and tinker. Now, to quantify what this means for CO2 sequestration, let's revisit an earlier calculation. Remember that we're trying to remove one pain point, the need for expert earthquake forecasting personnel. Now, before we needed 60% of the world's seismologists. Let's be conservative and say that our tool needs 10 times speed up after results have been analyzed. This still means one analyst can do the work of 10. And what's more, because our tool is more accessible, we can draw from a wider pool of talent. 600 analysts from a pool of 5 million people with basic computer science skills, that's a lot more feasible. Our tool is fast and easy to use, but you're probably still wondering how accurate and how reliable are the models? The answer is that it depends on how far ahead you want to forecast. We've designed different models that are reliable across a variety of timescales. From the plot on the left, you can see that the physics model, after examining 2 years worth of data, can forecast the general trend of seismic activity for another year. You can see, however, that there are also some gaps where it either over or underestimates in the short term. Now, we can address this with machine learning models, which we can fine-tune to give us very accurate predictions over much shorter timescales. This model looks at the past 16 days of activity and forecasts the next week. Note that these forecasts also come with uncertainty estimates that allow us to determine how confident the model is about its predictions. So where do we go from here? As any ML person will tell you, the biggest limiting factor for research is the amount of data you have. And for us, the frontier is all about working with more diverse sources of data. Thank you. At present, each model is very site-specific, which is an obstacle for sites that have collected less data. Leveraging more data also allows us to use more cutting-edge machine learning models to generate even more accurate forecasts. We're excited by 2 opportunities. The first is transfer learning, wherein one model is trained on data from multiple sites. Here we can combine the best of physics and machine learning to construct hypernetworks that predict the parameters for physics-based models. So the second promising direction is just to use more diverse data sets. At present, we're limited to sites that have collected injection data, but there's a wider catalog of unlabeled seismic data and also simulation data, which can be used for unsupervised representation learning. So let's recap. For CO2 sequestration to successfully combat climate change, it needs to scale up its capability to generate earthquake forecasts. Before FDL, the skill level required for this was a seismology PhD, and the total model preparation time was 22 hours. Now, just by importing SAFE, someone with basic programming experience can prepare a model in just 2 minutes on a tablet. We're eager to see what this increased speed and accessibility can do in the fight against climate change. Thank you very much.
Thank you, team. That was wonderful. And that was an extraordinary, wonderful ending to all of the team presentations for this year's FDL program. But we want to, once again, have some additional perspectives to help us unwrap these 3 presentations on physics-informed modeling. So let me introduce the panel who will help us unravel what we've just heard about from these 3 great presentations. Joining me and James is once again Masi Mascaro from Google Cloud. We also have Alexander Lavin from Pasteur Labs, Darren Damiani from the U.S. Department of Energy joining us as well. So welcome, everybody. And maybe, Alex, why don't we start with you, since I'm seeing you up there in the corner of my screen. And what did you think?
Yeah, thanks, Phil. Well, of course, I want to say thank you to the teams for the efforts and everything. It looks very elegant and smooth in the presentations, but behind the scenes, there's so much sleepless nights and hard work that they all put in. My perspective on this is exciting in a way where we are right where machine learning research meets an industry that is very unfamiliar to these methods, to any data-driven type of intelligence, let alone trusting those things to take them to the field. So having the conversations with mechanical design engineers and forward deployment engineers in the field, and talking to them, and just even trying to tell them what is data, how to build a machine learning model, let alone show them results and communicate results and build a system like the concentrated solar power system, where I recall one of the engineers saying, I don't want to deliver one design, I want a million. And just like, oh, we can generate synthetic data and give you a posterior of results and run optimization objectives over this. And those are words that that engineer has no idea what they mean or how to put them together, but we can build the thing and they can derive value. So that's the part that really excites me. And I think FDL is a unique opportunity to kind of cross that gap.
Yeah, that's a great perspective. And I think, crossing that gap is so important. And again, what's interesting to me about these presentations and these last challenges in particular is developing tools and techniques where the expertise that goes into the development is extraordinary. But one of the benefits is the expertise needed to deploy them is much less, which means they're more likely to be deployed, be useful and impactful. Darren, were you surprised by anything did you see that you saw? And what, from your perspective, are your thoughts regarding whether you were whether your expectations were met, exceeded, or underwhelmed?
Oh yeah, I mean, there's a common theme which is great to see, and that is that AI being used as a forecasting tool so that we can be more proactive in decision making as opposed to reactive, especially when it comes to hazards. In the presentation we heard earlier about the contamination tracking and for geologic storage for us in avoiding induced seismicity. But yeah, I think for the amount of time that the researchers put into this in 8 weeks, I mean, it's astonishing. They hit all the things that we're certainly looking for, right? This idea of taking complex information and processing that in a very rapid amount of time, so from 22 hours to a matter of minutes. But also addressing data sparsity. This is another common theme within the subsurface where you only have a limited amount of information. So how can you process that and get meaningful results? So yeah, quite astonished at the work they did, and very excited to see where all that goes later as we incorporate that kind of finding into our program.
Yeah, absolutely. And that's what's exciting, the actual deployment of what the team's achieved. And really, as you say, it's so much about decision support and seeing the future and reacting to that instead of seeing what's happening or what happened in the past and reacting to that. So time travel is really emerging. Massey, what are your thoughts?
Well, I'm blown away. I'm not surprised. But I mean, I want to actually also kind of point out something that I think is very important. I mean, the three problems that those teams resolved, I can't think of like three problems that actually are more important in today's world, right? I mean, if you think about energy storage, water, and CO2 sequestration, they're kind of really at the core, and applying AI to those is really important. I'm a physicist, so I love this idea of applying AI and physics together. I think it's really transformational because in many, many problems, we just can't use AI by itself. We either don't have the data or data gathering is clearly too expensive. I mean, think about this solar concentrator, the cooler optimization, problem. Like, I mean, we couldn't just build actually a lot of coolers just to gather the data about them. So the idea of using simulation and using what we know about the physics process is really transformational applying to AI. But also I love actually how some of the teams actually took this even beyond and now applied AI to speed up physics simulation, right? Yeah. And that actually is another kind of super transformative thing. So like, really congratulations to the teams. I mean, this is really kind of cutting edge, and it's really kind of applied to some of the most important problems in our world.
Yeah, absolutely. And I think you touched upon something interesting here, because it's not just about physics-informed AI, it's also about AI-informed physics, right?
Absolutely.
So, yeah, absolutely. James, some closing thoughts on your side before the fun of the awards ceremony?
Well, just to echo everyone's comments, really, we started FDL to tackle these sorts of problems, and just really, it's phenomenal to see real genuine traction, and hearing the comments from you all, so inspiring as well. And again, thanks to the teams. We're just about to change gears and go into the Innovation Awards, or sometimes we call them Collaboration Awards. It's a little bit hashtag awkward, because when we started FDL, we only had a few teams, and so there was easy enough awards to go around, and it was sort of fun. It's like everybody gets an award. But now we've got 13 teams, and we've still only got the same awards from when we started. And so there's a sort of, but the whole point is that everyone's done amazingly well. And this isn't about, it's not a competition. We use this word co-opetition. The reason FDL gets the results that it does is because we create a culture where everybody helps each other. And that's really the special sauce. That's the thing which, makes the difference. That's the thing that allows us to do what we do. So this is a thank you to everybody, researchers, faculty, but also the enormous community who've helped these teams get to where they have. And